Some years in, I earned a degree. I became a circuit designer where I worked for 3 or 4 years. And at some point during that time, I made a conscious decision that along the way, I had done both circuit design and printed circuit design. I made a conscious decision that I actually preferred printed circuit design to circuit design. It's just, I know some of you are thinking, what's wrong with this guy? But yeah, it was just a conscious decision I made. I really love that field. And I've been in it ever since. About 17 or 18 years into my career, sometime in the 1980s, we started seeing noise and interference issues in our circuits. And we had no idea why, because we had changed nothing in our designs. I mean, we hadn't changed our clock frequencies, we hadn't changed our layout practices, we hadn't changed our packaging, nothing. We had done nothing different, but all of a sudden, we were seeing interference problems. And frankly, at the time, we had no idea why this was happening. Not a clue. I mean, we were just completely clueless as to the cause. And worse than that, we were clueless of how to fix it, how to stop it. I mean, every time a problem would occur, and it wouldn't happen on every system, but every 5 or 6 systems that we would design, one out of those 5 or 6 would rear its ugly head, and we'd have internal interference problems, or we'd have EMI problems, or whatever. And we had some older guys like I am now, older wizened guys, which I'm not, who would tackle the problem each time a problem would occur, and they would generally find some kind of fix that they could implement into the design to basically heal the problem, if you will. At least we thought we were healing it. And what was really funny, because we didn't understand the motivation behind why this was happening, looking back now, I know exactly why it happened. It happened for 2 reasons. One, because we were clueless about board design, absolutely clueless. But the biggest reason, that and the other reason it happened, was because rise times were getting faster. I hope all of you know that clock frequency has nothing to do with your problems. Nothing. It's all about rise and fall time of signal outputs. Everything that goes wrong, crosstalk, signal integrity, EMI, any kind of interference, I don't care what it is, it all happens during the rising and falling edge. And because rise times were getting faster in the 80s, that's why we started seeing problems. And of course, eventually we learned how to heal it, but it took us a long, long time. Each of these fixes that we would do, that we would come up with, management deemed as the holy grail. And they decided this will be in all future systems, amen, thank you. And so we would install it in our next system, and 3 or 4 systems later, we'd have a problem, and this fix that we put in did nothing. Because it wasn't a fix, it was a Band-Aid. These weren't fixes, we were fixing nothing. We were throwing lots of bandages on a hemorrhage that was bleeding like crazy, and all we did was slow down the bleeding so we could ship the product. We absolutely didn't understand why. And frankly, at the time, I thought we were the most ignorant bunch of fools on the planet. Really, I worked with 7 or 8, 9 other engineers over that period, and I thought, what's wrong with this? How is it the rest of the world gets this and we don't? Well, I found out that wasn't necessarily the case. In the 1992-ish time frame, sorry about my voice, I've been speaking for the last 2 days and it's kind of shot. In the 92-ish time frame, EE Times, I believe it was EE Times, wouldn't swear to that, came out with a survey for engineers. And they asked a bunch of questions. What do you think about your career, this and that, yada, yada. One of the questions they asked, and this is the question that motivated me to fill out the survey. What was missing from your college education that you desperately wish they had provided? Over 80% of the people, and there were many thousands of responses, over 80% of the people who replied to that said, I wish I had learned something about noise and interference, what causes it, most of all, how to stop it. Not how to fix it, not how to Band-Aid it, how to keep it from happening by design in the first place. And when I saw that, I realized, my God, we're not the only idiots in the world. There are lots of us who are idiots. It isn't just us. I made a decision that day. That was a fateful week in my life. I made a decision after that this isn't advancing, because I'm pushing the wrong button. That's why it wasn't advancing. Funny how that works. See, if you don't operate the equipment right. I made a decision that day, that week in my life, that I was going to figure out, I was going to decide, I was going to find not Band-Aids, but real solutions to noise and interference and EMI and those sorts of problems. I probably spent about the first 10 years just getting a polite understanding of it. I started buying books. Actually, I bought a few books before that. I had Henry Ott's Interference Technology book and a few others like it that I had bought back in the late 80s, early 90s in an attempt to try to get my arms around these issues. And once I made the decision to do this, I started buying books at a rate of 5 or 6 a year. I now own over 100 books on EMI, high-speed design, interference. If anybody has written a book on this subject, I own the book. Anybody, I don't care who it is, Howard Johnson, Dr. Bruce Archambault, Eric Bogan, you name it, I have all their books. I've read them all. I've read some of them 3, 4, 5 times because the information in it is invaluable. Anyway, during that first 10 years, all I really did with all that reading was gain a good, polite understanding. I didn't really grasp the concept. About 12 or 14 years ago, a gentleman by the name of Ralph Morrison attended a class of mine in California. It was a one-day class, and at the end of the class, he came up to me and he said, "Rick, I'd like to, if you would, can we have dinner together?" I said, "Sure." And over dinner, he proceeded to tell me, he said, "I liked your class today. You have a lot of good stuff in it. And you've obviously worked hard to put it together." He said, "Obviously what we're trying to do here is slay a monster. We have a monster in the form of interference in EMI that we need to tame. And you're obviously trying to slay that monster." He said, "The problem is you're slaying the wrong monster." And I said, "I'm sorry." I mean, talk about being shaken. I thought, what am I mean, I've spent years developing this expertise. And I said, "What do you mean, Ralph? What exactly am I missing?" And he asked me a question. He said, "What is energy?" I said, "Well, energy is probably the movement of molecules." I concocted an answer that was kind of like this. It didn't really match that statement. That statement is out of a physics book. But it was something to that effect. I didn't quite get to that point. And energy, of course, exists in many forms. Mechanical energy, light speed, light, sound, electrical energy, yada, yada. He then asked me, "Where is the energy in a circuit?" He said, "Is it in the traces? Is it in the voltage? Or is it in the current?" And I paused for a long moment and I thought, I said, well, in a power system, for example, if energy are molecules in motion, you look at the power system, it's basically a DC voltage, more or less, with AC currents, high frequency, low frequency, varying frequencies, but the currents are what's in motion. So I said, the energy must be in the current. And he said, "Nope, incorrect, sir." And I said, "Why is that?" And he said, "The energy is in the fields. The energy is in the electric and the magnetic fields of the circuit." He said, "There is no," and I've since verified this, he said, "there is no energy in voltage or current. The energy is in the fields. The voltage and current are generated by the fields." I had a friend from Sweden whom I talked to last fall on a topic, and we were talking about this very issue, and he said, "Yeah, I liken this to astronomers." He said, when astronomers are studying black holes, they can't see the black hole. All they can see is the impact it has. And so that's what they look at. They look at the gravitational fields that it generates. They look at the gravitational pull it has on things around it. And they can tell from that its size and strength and yada yada, because they can't see the black hole. We can see fields, sort of, but it's a challenge to pin them down all the time in a circuit. It's easy to look at voltage and current to tell how much power we have, what the task is we're accomplishing, and so on, to see where it's moving and yada yada. And that's what voltage and current are. They're the byproduct of energy, not the energy itself. He then asked me, where are the fields in a circuit? Are they in the traces or maybe in the planes? Now I was really stuck and I went, I don't know. And he said, neither. The fields are in the dielectric of the board. The fields travel through the plastic and fiberglass. So what he was telling me is all of the energy does not travel through the copper, it travels through the plastic and the fiberglass. People think when they design circuit boards, they're designing traces, routing traces, placing parts, routing traces. You're managing dielectric spaces. And if you don't manage them properly, you will have energy spread that will cause noise problems. Example, if I have two traces on a one-layer circuit board that are like this, far apart, a forward and a signal and its complement, signal and its ground, call it whatever you like, there's going to be a broad space between them. There's going to be a large volume of fields associated in the dielectric space with these two traces. Anything I get in this region is going to pick up the energy from those fields and it's going to transfer to that circuit. And that's going to show up as interference. I can control that by moving them close together and shrink the fields to a very small size and keep a tight volume. So it's important to understand where the fields are because that's where the energy is. Whenever we route a circuit or a trace on a board, we're routing half of the transmission line. We're routing the forward half of the line. The return half of the line is the ground plane, the power plane in some cases. Can you use a power plane? Somebody? Anybody?
Yeah.
Sometimes. Yes, you can, and no, you can't. You can and you can't. There are times you can, and there are times you can't. Let me give you a quick example of when you can't. You have a 3.3 volt signal. Can you reference it to a 5 volt plane?
Yep.
You damn well better not. You want to talk about energy spread? Oh my God. Do you do that in your boards accidentally sometimes? You just might. Pay attention. Look closely. Let's have another example. I got a call one day from a company near where I live. And they said, Rick, we have a 2 gigahertz signal routed on the top of the board. It comes in from a preamp and is amplified at the preamp and then sent into the board to several locations. And when the signal level gets below 500-600 millivolts, we're seeing serious interference issues, and we're not sure why. And I said, well, let's take a look. So I went to their place, and we looked at the circuit, we looked at a lot of stuff. And make a long story short, I finally said, let's look at the board stack. And as we did, I said, what is driving these two amplifiers? And the guy said they're both driven from 12 volts and ground, and they're on layers 3 and 4. And I said, then what's on layer 2? Is that a ground plane? And he queried layer 2 in the CAD system and said, no, it's a 5 volt plane. And I said, aha. And he said, aha. And I said, there's the problem. And he said, what do you mean? And I said, where is the return current from the signal on layer 1? And he said, well, it's driven by 12 volts and ground. He said, I suppose it could be at either of those planes. He said, I would hope it's in the ground plane. And I said, no, it's not. It's in the 5 volt plane. And he said, what? And I explained to him why. I don't have time to explain this to you right now, but energy takes the path of least impedance. It will, the fields, the energy, will always couple to the path of least impedance. And that is the 5 volt plane. There will be no energy in that plane above the audio range. Now, when you get down on the audio range, things change. Currents take multiple paths sometimes. You have to be very careful with audio signals, how you route the return path. People think high frequency is hard to design. I've designed 16 gigahertz and it's a walk in the park. But audio, ooh, you really have to be careful with return paths in the audio range. And most people don't do it right, by the way, just a thought. I explained to him that current takes the path. So he said, all right, Rick, if that's the case, when it gets back here, when the return current gets back to the driver, how does it get back in the driver as a return? And I went, aha, there's the problem. The fields occupy the space. By the way, I hope all of you know this too. When you send fields down a dielectric space, they form a forward current in the trace, and they form a reverse current in the return path at the same time. A lot of people think the signal goes down the line and comes back on the ground plane. Oh, no. The currents are formed simultaneously in both directions. So when the return current sitting here is trying to get back into here, the only choice it has is to spread out across the top of this plane, the fields, spread out, trying to find a path to layers 3 and 4. And they find via holes that won't go through the plane, by the way. Fields do not penetrate planes. A plane offers 60 to 70 dB of isolation to high frequency signals. 60 to 70 dB. So the fields find via holes, they couple through the via holes, they get down in the dielectric space between layers 2 and 3, they then get into the 12 volt plane, and most of the return current then will couple into the amplifier through the 12 volt plane. Some of it does couple down to the ground plane through via holes, but most of it goes back through the 12 volt plane. And he said, so what are we gonna do about this? I said, first off, why is there a 5 volt plane there? And that's a long story, which I won't get into, but we figured out how to resolve it. They changed this to a ground plane and all of the problems went away. Because now they had a direct path to the ground back to this device. Very simple, very specific. The transmission line is any pair of conductors used to move energy from point A to point B. The energy flows through this dielectric, it creates voltage and current here and here. People ask me all the time, why is there loss tangent? Because the energy moves through the dielectric, and dielectric is an imperfect conductor. Some are better than others. The high frequency materials designed for high frequencies are better than materials like FR4, for example. That's why there's loss tangent. All the energies in the fields. How you treat this, oh, does it matter? Oh boy, does it matter. These are what the fields basically look like. This is a hyperlink simulation, and it's a very accurate depiction of fields, and that's why I chose to use it. Not because it was a mentor thing, just because I felt it was accurate. You'll notice the fields do spread out a little bit. They don't stay tucked completely around the trace and the plane in the dielectric space. They do have some spread to them. And that's why we have crosstalk. When we get traces close enough together versus height above the plane, the fields couple into one another, and you get crosstalk. So you're gonna have some energy coupling no matter how well you design, because it's very challenging to design a perfect circuit board. So, 2014, I started saying 1914. I'm not quite that old. 2014, I went to the IEEE symposium, where, by the way, Henry Ott was a keynote. And going back just for a second to the point about all of us at our company not understanding interference in EMI. At the keynote, Henry said in 1989, he and the IEEE created a survey that they sent to every college in North America, the United States, Mexico, and Canada, all of them. And they asked the question, do you teach anything in the way of EMI to your undergrad students? 5 universities said yes, 5. There are many thousands of universities. And Henry stood there, hung his head and said, it isn't much better today. There are more than there were in 1989, but not enough, not nearly enough. Dr. Wu presented that year at the IEEE MC Symposium, and he had this slide in his slide set, and I loved it. I thought it was really spoke loudly. There was a room of about 100 people, and he said, which of these 4 boards, now this is layer 2 of a circuit board. This trace is on layer 1. You get the picture, it's a microstrip, right? Which of these 4 circuit boards has the best EMI signature, which is second best, third best, and which of the 4 is worst? Most of the engineers, about 75 to 80% of the engineers in that room said figure 4 was going to have the worst EMI figure. Probably followed by 2, and then 3, and then 1 would be the best. Let's have a look at that. Here's 1 and 3. Well, they were right about that. 1 was the best. 3 was very close to it. Very, very close to it. Here is the other one with a crosshatch plane. And here's the one where they routed across the split. This is 2, that's 4. This is 2, that's 4. A crosshatch plane isn't nearly as bad a thing to route across as a split plane. Just so you understand the concept, whoops. There's a thing called a microstrip coupled slot line fed antenna. It's what people do when they want a circuit board to radiate like a radio station. And the design looks exactly like that. That's what a microstrip coupled slot line fed antenna looks like. So when you listen to analog devices, shame on you, and you split the ground plane because they tell you, oh, you must, app notes are wrong. When it comes to board layout advice, app notes are wrong at least 80 to 90% of the time. Just a thought, just a thought. When you listen to them and you route across that split, you create an antenna. Let's look at currents and fields. Here's the current in 1, and here's the current in 3. Why do those look so identical? Because case 3 is routed across a solid ground structure. It's every bit as good as 1. That's why it looks like 1 in terms of its EMI signature. This one causes some amount of field spread as you have to go around the openings in the plane. But look how much, it's not a whole lot worse than 1 and 3. Look at this thing. That's why its EMI signature is 30 dB greater than 1 and 3. What happens when you route across a plane that's split completely? Back before I met Ralph Morrison, I used to think that the return current took this path right here. I knew there was field spread, and that's why I thought it occurred. Not true. The return current gets to here and goes, uh-oh, I have no way across this moat. So it creates it spreads out across the entire length of the slot and creates as much capacitance as it can through the dielectric of the board. And if that's not enough capacitance to create a large enough displacement current to get the signal current across the gap, then the fields start expanding up above and below the board into the air, using air as a dielectric for a capacitor. And they will expand as far as necessary to create the adequate displacement current to make the return path happen. We have actually measured fields on boards above split grounds as high as 6 inches to a foot above the board surface. Well, if they're that high up, how far spread out across the board do you think they are? What do you think the risk is that that energy got out of the box and is creating a problem? You see the point. A study done by Dr. Bruce Archambault, he designed a 4-layer board that had a driver on layer 1 with a ground plane on layer 2 and a receiver on 1. And if you guys don't know who Dr. Bruce Archambault is, you should. He has a book. I'm gonna leave I have about 10 cards left. I've been in Massachusetts all week. I'm just gonna leave them here. If you want to know more about Archambault, email me. I'll tell you the name of his book. It's better than Gone with the Wind. It's the best book I've ever read. Anyway, Bruce put a trace on layer 1 of a circuit board relative to route layer 2. He measured the radiated energy coming off the board in the near field. Now, the energy level was high because he was measuring it in the near field, not in the far field. He then turned off this driver and receiver, and he turned on a driver and receiver on layer 4 that exactly matched the one on layer 1. Except the one on layer 4 routed across a split power plane. He then added capacitors, because everybody knows all you got to do is put capacitors across those splits, and by George, the problem solved, right? So he added capacitors and he measured again. Then he added 2 more capacitors and measured again. Here's the EMI signature against the ground plane. Here's the EMI signature crossing the split. Looks to me to be about, 20 dB worse. That's a significant number. First capacitor added, it got much better at low frequencies. Just as bad above 500-600 megahertz. Well, we don't have 500-600 megahertz energy in our system. Oh, yes, you do. If you're using today's processors, FPGAs, memory devices, whatever, I don't care if you're clocking at 1 cycle a day. Once a day, you have gigahertz level energy in your system. Because frequency is equal to 0.5 divided by rise time in nanoseconds. Today's rise times are 3, 4, 5, 6, 700 picoseconds, typically for almost every device you buy. 500 picoseconds equals 1 gigahertz. 250 picoseconds is 2 gigahertz. Every time you hammer a transmission line, you're putting high frequency energy in. Think about that. Here's the second capacitor added. It improves things a little. But you can see at high frequencies, it's still almost as bad. Why? Because capacitors don't work at high frequencies. They run out of gas. If you look at the impedance plot of a capacitor, it does its best work at its self-resonance, which for a 0.1 mic cap, 04, 02, 02, 01, whatever, you're talking anywhere from 10 to 50, 60 megahertz. Megahertz? Yes, megahertz. At 5, 6 times that, this thing's an inductor, which is why these plots look like this. Because once you get to 5 or 6 times the self-resonant frequency, you're out of gas. Here's another example of bad design. This was a study done 12 years ago by the ever-present, always wonderful Dr. Howard Johnson. It's called BGA crosstalk. He chose these two parts because internally they were almost identical. Same voltages, same number of gates roughly, same operating conditions. They were very nearly identical parts, except they had different pinouts on their lead frame. This one here was 5 times noisier than that one. Why? Because it doesn't have adequate return path. Where do you think this signal right here, where do you think its return path is? You think it's one of these powers or grounds? No, it's these 4 signals right here. If there's no grounds nearby, the signals use each other as a return path. That's how this works. So when you buy an IC, you don't buy this stuff, you buy this stuff. You guys as engineers, when you're looking, you need to look hard. You want the interference and the EMI issues to stop? Look closely, not just at your board design, but at the ICs. It's all about packaging. It's not about what you put in the schematic. It's about how you design the thing mechanically and physically. It's the physics you put into the board and the IC. Here's an IC that's wonderfully designed from Freescale. Every signal pin is 1 pin's distance away from power or ground or both. That is a good design. That's what future ICs need to look like. When you're routing and changing layers, I'll try to be swift here and brief. When you're routing and changing layers, if you have layer 1 routed in the X direction and layer 3 in the Y and the next, and so on down through the board stack, when you want to change directions, obviously the best place to go is layer 3. Why? Because the fields travel in this dielectric space, creating this forward current and this reverse current. And when the fields get to this point, and there's a via as a wave, by the way, transmission lines are waveguides. Oh yeah, RF engineers have waveguides. Yeah, so do you. Every circuit board you design is a waveguide. Every one of them. Every trace you route is a waveguide. That's why it's important to have the right return path. Anyway, when the energy gets to here, it couples through the hole and continues on there, and you basically get no spreading fields. You get no field spread that leads to issues. If you have to go from the top, say, to the bottom of a higher layer count board with ground planes on layer 2 and the layer next to the bottom, you need to put a ground via next to the signal via. Now, an academic would tell you every signal via needs a ground via. See, I designed boards all my life. I'm a realist. I know that that's really not possible. The last design I ever did at L3 was a 3x4-inch board that had 2 1300 pin VGAs on it and 8 other VGAs and 1300 other components on a 3x4-inch board. We just didn't put a ground via next to every signal via. It just doesn't work that way. But you put as many as you can, as close as you can. Because when you do, you contain the fields. Here's another picture from Dr. Howard Johnson. The fields are traveling through here. The return current is here. The forward current is on the bottom of this trace. There's an error in this drawing, by the way, which he would faint if he heard me say that, but I'll point it out in a moment. The fields are here. They couple through the hole. The fields go through this dielectric space right here, down through this dielectric, couple back through this hole, and continue on. The return current goes up the outside of this via barrel, and the error in this drawing is Dr. Johnson shows the forward current going down through the center of the via. There is absolutely zero current inside of the via because of skin effect. The fields create the currents on the outside of the via. People ask me, can I fill my vias? Won't that affect current flow in the via? You can fill it with peanut butter. I don't care what you put in it. It doesn't matter because there's no current flow in the via. It's on the outside of the via, both vias, and that's the error in this drawing. If you have to change layers between a power and a ground, how do you do it? Well, we've already shown that the decoupling cap will help. It'll take the low frequency energy up to 250, maybe 300 megahertz and couple it through just fine. So the decoupling cap helps a lot. It gives us a lot of good stuff. But what do you do beyond 200-300 megahertz? How does that energy get through there? Well, if you have the planes close enough together, if the planes are, where is the number? 8 mils or less separation, and this is an arbitrary number. It's basically, we did a lot of experimentation when I was in the telecom industry, looking at just how far apart could we separate the planes and change layers from a power to a ground before we got so much field spread that it started to affect our EMI signature. And that's kind of where that number came from. You know, is it exactly 8 mils? No, it's in that vicinity. Okay, so when they're roughly 8 mils apart or less, basically what happens, the fields go through here, they spread out in a circular fashion to create a dielectric, a displacement current through the capacitance of the planes. And if the planes are close together, they don't have to spread far because there's a lot of capacitance. If the planes are far apart, like they are on a 4-layer board, and you're asking, why are the planes far apart on a 4-layer board? Can't we put them close together? The answer is no. No, you cannot. I mean, if it's not a 62 mil thick, 1.57 millimeter thick board, yes, you can. If it's a half millimeter board or less, sure, you can have the planes close together. In a conventional 1.5, 1.6 millimeter board, no, you can't have the planes close together in a 4-layer board because that's how they manufacture. Now you can pay extra and get them close together, but you're paying for 6 layers. Why the hell would you pay for 6 layers and get 4? I mean, you see the point. So it's a no-no. So if you have a 4-layer board, there's so little capacitance between the planes of a 4-layer board because the planes are separated by anywhere from 3/4 of a millimeter to a millimeter. And the plane, the field spread out for multiple inches. Well, what if there are other vias? What if there are other signal vias here and 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 here? All of those fields are all spreading their energy out. And all of those fields couple into one another saying, hi, how are you? Hey, great, how are you? Good, nice to meet you. And they couple common mode currents all into one another. And if some of those lines go to a connector off into a cable, well, you're gonna fail radiated emissions. I'm sorry to tell you, but that's how it works. So don't do this. People say to me, hey, wait a minute, Rick. We know that Intel and AMD used to make 4-layer motherboards and they worked. Yes, you know how? They didn't change layers. They stacked the deck. I worked at AMD for a year or more, back in the mid-90s when they were developing the K7 processor. We would lay out the IC pinouts of the processor, the North Bridge, the South Bridge, all the memory devices, everything, so that all of the buses flowed. You ever notice what the bus flow looks like on a motherboard? It's amazing. How do they do that? Because they stack the deck. They pin out the ICs so they do that without changing layers. The only thing that changes layers are low frequency control lines. That's how they get away with it. You probably don't have that option. Why do they make motherboards? To sell ICs. They give their motherboard designs away. They'll spend $2-3 million developing a motherboard. They'll give the design away to manufacturers of computers. So if they use that motherboard, they have to buy AMD ICs to populate it. Intel does the same thing. They all do. Great business, isn't it? Board stacks. What kind of board stacks? I'm almost done. What kind of board stacks make sense? Okay, let's talk about that. I said 4-layer boards with power and ground on them are a bad idea. Power and ground on 2 and 3 are a bad idea. So what can you do? Well, in 1995, we had just such a board that was failing radiated emissions by a pretty hefty amount. It was the only operational board in the system. There was a power supply board and a couple of little things in there, but it was the only thing doing anything. So we knew it was the culprit. And after a long discussion, I was in aerospace then. After a long discussion, we decided to put our ground planes, pour ground on the outer layers between all the components, route all of our signals on layers 2 and 3. And what was really funny, before we changed the signals to the inner layers, that board was packed. I mean, the combination of ICs and signals on 1 and 4, man, it was just like, wow, there's no place to put anything. But when you move the signals to the inner layers and you don't have all those pesky components in the way, there's room like you can't imagine. So we poured all of our power with the signals. We had to move a few signals around to get all the connections. And all of a sudden, all of our problems went away. 2 reasons. One, we made everything strip line, so we got rid of differential mode EMI. But the biggest reason, we improved the high frequency impedance of the power bus. People think, yeah, you need high interplane capacitance. You want close set planes on the inner layer of a board, not for high capacitance. You want it for low inductance. Capacitors will give you low impedance at frequencies up to 300, 400, 500 megahertz. Beyond that, you need low inductance, and you're not going to get it from capacitors. You get it from the impedance, the inductance of the planes being very, very low. And the closer the planes are together, the lower that inductance will be. And by changing the planes from 2 and 3 to basically having this power reference here and this power reference here, all of a sudden the impedance of our network in the power bus went down by a factor of 5, 6, or 7. And everything just immediately started to work better. Here's another example of a 4-layer board that I tend to prefer. Power and ground on 2 and 3 is a very bad idea. Here are 6-layer boards that are very poor. I'm almost out of time, so I'm not going to explain why this one is. It has to do with common mode currents, but I'll leave it at that. Look at here. Power and ground. When you pull power out of the power bus, what happens? Well, you're pulling fields through this dielectric space, right? Well, guess what? You also have signals operating in this dielectric space. And you have signals operating in this dielectric space. So every time you pull power out of the power bus, you're spreading those fields out across the power bus and coupling into every single signal that's on the inner layer of that board. This is the single worst board stack you could possibly ever in your lifetime use. There is no worse board stack. Now, there's a solution to it, and basically the solution is this is the solution. Basically, make 2 and 5 grounds instead of power and ground, pour your powers here, and with all the signals, and you'll completely eliminate the problem. And you also don't have to worry about changing layers relative to a power plane because everything references ground. Think about it. All the signals reference ground. This is the same thing here. This is a 3-signal layer, 6-layer board. 3 signal layers on a 6-layer board. Referencing ground, referencing ground, referencing ground. Power, poured power references ground. Low power bus impedance, excellent routing technology. This is a low noise 6-layer, so is that. 8-layer designs, an excellent 8-layer design. Power and ground in the center, ground here, power's poured on the other layers. Here's one I also like, all the planes being ground, all the power is poured on signal layer. And if you can't get all the power distributed on the signal layers, yeah, then maybe add a ground plane here or some power in there. This is the last slide. This is a 8-layer board stack up recommended by a major, not going to mention their name, IC company. It was the processor we used on that little 3x4-inch board. And their app note said, if you want to use an 8-layer stack up, here's an excellent 8-layer stack up. We built this and made an evaluation board and it worked just fine. Well, I'm going to tell you, with enough on die and on substrate capacitance for power delivery, yes, I could believe this could work. But I can tell you with clarity, there's no way they can pass EMI testing. Why is that? Because this power plane is going to have some of its fields coupled to this ground, and some of them, more, are going to be coupled here because this distance is about 2/5 that distance. Which means 3/5 of the energy from this power plane is going to be in this dielectric space, making return currents on power plane 2. Now, how is that going to get back to the source using power plane 2 as a return path? I ask you. Even worse, Look at these signals. You also have power being generated in this dielectric space, coupling energy into those signals. So one guy said to me one time, well, just make this core thick and put the power planes far apart. And yes, that would certainly help, but you still have this power plane moving all of its energy through this dielectric space, coupling into the fields of all of those signals. There is no way you can turn this into a good board stack. It's terrible. Thank you very much.